Okay, so this is what we want. Before we get there, we have to look at this real quick. A couple of FYIs, we're gonna need it for this exercise. So the integral of 1 over x plus 1 dx, that's actually just the natural log of x plus 1, because if you take the derivative of this, remember that the derivative of natural log is just the reciprocal of whatever this is. And that would just be this, right? Because the derivative of that would be 1 over x plus 1 times the derivative of the inside by the chain rule, but the derivative of the inside is just 1, so it's 1 over x plus 1, which is exactly what that is. So let's just keep that in mind. That's the integral of that. Now what about this one here? So the integral of x over x squared plus 1, well, watch. Here's the proposition. I propose to you that we're going to need this here, because if I take this derivative, I'm going to get 1 over x squared plus 1 times the derivative of the inside, which is 2x. So you see how that matches almost perfectly there? How that this is almost identical to that? It's just that that 2 has to be gone. So what I'm going to do is I'm going to put a 1/2 right there. Because if there's a 1/2 there, when I take the derivative, the 1/2 would still be there, and it would knock out the 2 that gets created at the end. And when those are gone, it'd just be x over that, which is exactly what that is. So keep this one in mind as well. And then one last one down here, that's actually just the derivative, or I should say that's the definition. Tangent inverse of x, right? That's just like a textbook formula. This integral is just tangent inverse of x. And of course, all of these should be plus c, plus c, plus c. Let's leave that alone for now. These are going to come in clutch in just a moment. For now, let's go back here. We want to take this integral, but we don't want to do it like that. We want to break this apart into smaller integrals and just go term by term integration. So what we're going to have to do is take this piece and break it up into smaller pieces. Now look, a quick FYI here. I have these written beforehand. Note that this here, this fraction, can be ripped apart into 2 fractions. 2 fractions because the denominator had 2 factors. 2 factors like that. See, one goes there, this one goes here, and just call it A and B. This one here has 3 pieces. So I go 3 pieces, one of each, and I go A, B, and C. Now this one's different because if you notice, there's 2 pieces, so there's 2 fractions, but this one is a power of 2. So watch. For these guys here, notice that these are all linear. These are all powers of 1s. And if it's powers of 1s, the numerators are constants. So here, this x plus 3, that's linear. It's a power of 1. So the numerator should be a constant. However, this factor is not linear. It's quadratic. And so the numerator has to be 1 power less than the denominator. Since this is a power of 2, upstairs I need a power of 1. So we go bx plus c. You see what I'm saying? So if the denominator is linear, the numerator is constant. If the denominator is quadratic, the numerator is like a line, linear. So keep that in mind. Let's actually do this problem here now. So now going back to the main problem, I recommend that we take the integrand and rip it apart into smaller pieces, and then we can integrate term by term. So it's nice that the denominator was already fully factorized. Now we have 2 terms, so we're going to have 2 fractions. And based on the discussion we just had, since this denominator is linear, the numerator is constant. Since this denominator is quadratic, the numerator is linear. Just bx plus c. Now what we want to do is we want to make this equation less complicated. So what we're going to do is we're going to wipe out all of the denominators. And in order to accomplish that, we're going to take this denominator, copy and paste it in each of these numerators. So we basically multiply both sides of this equation by x plus 1, x squared plus 1. And the reason that's good is because watch what happens. These knock out, and then these knock out, and then these knock out. And so here is what we're left with, right? So some teachers call that a fraction buster because you wipe out all the denominators. So these are the pieces that survived, right? The a is there along with that piece that's left over. The bx plus c is still there along with the x plus 1. So why don't we distribute there and apply the distributive property there? Okay, so distributed the a, carefully expanded this product there. And why don't we group pieces alike? So I pushed the thingies with x squared to the front, and then the thingies with just x, and then just the constants. Now watch what happens here. So I took x squared and I factored it to the back, so it's a plus b. And then here I took x and I factored it to the back, little typo there. And then inside is b plus c. And then a plus c is still in the front. Now watch this here. So you see how on the left-hand side, that's still equal to 1. But the reason I inserted these zeros is to make a comparison. Let's compare left with right. Notice how on the left, the coefficient of x squared is 0. Here, the coefficient of x squared is a plus b. Here, the coefficient of x is 0. Here, that's the coefficient. And then there, the coefficient is 1, or the constant is 1. And here, the constant is this. So what I'm saying is 0 equals that. 0 equals that. 1 equals that. We create a system of equations just using good old-fashioned logic when you compare the left with the right. So from this one equation, we can extract this system of equations here in blue. So I wrote down this system here a little bit bigger to make it easier to look at. Now, why don't we do this? Why don't we move this a to this side? So that would say that b equals negative a, right? If I move that to this side. And then let's write this equation again. But instead of b, we can write negative a. So let me take negative a, which is b, and drop it in right there. That would say that negative a plus c equals 0. And then why don't I take this equation here, write it down here, negative a plus c equals 0. And why don't I copy and paste this guy underneath it? And then what we can do is we can actually take these equations and add them together, because these would eliminate, they're gone. And then c plus c is 2c equals 1, which implies that c is 1/2. Now, since c is 1/2, you can plug it in there, that'd be 1/2. You can subtract 1/2 from 1, revealing to us that a is also 1/2. And if a is 1/2, you can drop it off there, and that will imply that b equals negative 1/2. So these little system of equations are kind of cute, and they always have things that look like this, half, and then c is 1/2. Now, what was the point of doing all of this? The point was we took the original integrand and ripped it apart into two smaller fractions. And now we can go back with a, b, and c and deposit these values into those fractions. So what I'm saying is take a, b, and c and plug them back in for a, b, and c using these green values. So if we go back to the original problem here, the very original problem that was in the book, 0 to 1, instead of writing this one fraction, which is that, we can write the two smaller fractions that we discovered together like this. So you see I have the integral from 0 to 1, that's still there. The dx is still in the back. And then all that stuff there gets replaced by this here because, according to this, they are equal. That one fraction got ripped apart into two. System of equations give us a, b, and c. Plug them back in. Here is what we have. Now look, that addition, why don't we just go the integral here plus the integral there? Okay, so I gave each piece its own integral, dx, dx. And now you see that 1/2, let's kick it out to the front. And you see the 1/2, let's factor out a 1/2 to the front as well. All right, so let me explain what just happened. That 1/2, I kicked it out to the front, and the dx got kicked up to the front if you want to, or you can just leave it in the back, doesn't really matter. That stayed the same, basically. I actually took out a negative 1/2 from the numerator, and I kicked that negative 1/2 to the front. That's why it's right there now. But if you take out negative 1/2 from the numerator, you're left with x minus 1. The bottom, I left it the same, and it's still dx. Now this part here was kind of tricky. Let me explain what I did. If you have like a plus b over c, that one fraction can be ripped apart into two, where the numerator, each term in the numerator gets the denominator, so it's like a over c plus b over c. So you break it up into two. I did that right here. So you see how this is x minus 1 over that. So I said x over that here, and then minus 1 over all that. There. See what I'm saying? So the negative 1/2 was just there, and I put green brackets because this one piece got ripped apart into two, so that the negative 1/2 has to distribute to both of these pieces that were just created. And it's minus because that was minus. So again, it was x over that here, and then negative is there, and then 1 over that is there. So now let's take the negative 1/2 and let's distribute to both of these pieces. So I distributed the negative 1/2 to there and to there. The double negative became positive. Now, why don't you look at, let's say, this here, look at that there, and look at this here. Those should look familiar. Those are the FYIs that we did at the beginning of this video. Now, this here, that is this guy. So that integral just becomes ln of x plus 1. This in the middle, that's exactly this piece, so that becomes that there that we said. And then in the back, that piece becomes tangent inverse. That says x squared plus 1, which is the same as that. So we're going to keep the halves in place. It's just the three integrals become this, this, and that respectively. So just a quick comment, that negative 1/2 was there, but there was another 1/2, which was, that thingy that we discussed at the beginning of the video. So now let's see, all of this is to be evaluated from 0 to 1. Those are the limits of integration, 0 to 1. So we have to take 1 and plug it into all the x's, and then minus, then plug in 0, and plug it into all the x's. So I plugged in 1, boom, 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 plugged in 0, boom, 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 they're being subtracted. It turns out that this is 0, that is 0, and that's also 0. All three of these are 0. Sometimes that happens, so those are gone. We're left just with this right here. Now look, the absolute values are just there in case you have a negative number, but it was 2, which is positive, so I dropped the absolute values. That's here, that's there. Now plus 1/2, and then on a calculator, type in tangent inverse of 1, make sure it's in radians, and it'll say pi over 4. Okay, so that's just calculator. Now look, remember properties of logarithms where a coefficient can become an exponent. So if you have natural log, this 1/2 can become a power, and this 1/4 can become a power. Remember another property of natural logarithms where if natural logs are being subtracted, you can take those two natural logs and combine them into one, but it's going to be the top, it's going to be that on top of that. So it'll be 2 to the 1/2 over 2 to the 1/4. That's just properties of logs. And then remembering properties of exponents, if you have the same base with a different power, you can combine those two things into one, but you're going to have to go the top minus the bottom exponent. So it's natural log, but instead of a fraction, it's just going to be 2, but it's going to be 1/2 minus 1/4, like that, plus pi over 8. And of course, 1/2 minus 1/4 is 1/4. So final answer, we have pi over 8. And 2 to the 1/4 power is the same as the 4th root of 2. So I'm not sure if you're supposed to turn in a decimal, but if you want the exact answer, that is it right there.